And now it is my great pleasure to introduce Kang Kuen is a professor at Harvard University. She's really a pioneer in ultracold molecules, studying ultracold molecules using AMO techniques, studying ultracold chemical reactions in the quantum regime. And she's really pushing the frontier of this field and is now developing new techniques, I would say revolutionary techniques, to really assemble single molecules atom by atom using optical tweezers. Her great contributions have been recently recognized with the Rabi Prize of the American Physical Society in 2019. And now I'm really excited and curious what the latest developments in this field are. And I look forward to your talk, Kuen.
Hello, thank you for joining me at this talk. I am excited to tell you about a research direction we have been pursuing for a number of years, where we build single molecules from single atoms for quantum science applications. Let me start with a brief motivation. A goal in quantum science is to create quantum systems for simulation and computation using qubits that are fully controllable, scalable, and can be entangled to perform logic gates. Already, a variety of physical systems can reach this goal to a certain degree, as shown in these pictures. Ions, superconducting qubits, atoms array in tweezers or optical lattice, and many other systems. But of course, there are still challenges ahead, and one major challenge is to create very high fidelity entanglement in a scalable system. My group have been interested in tackling this challenge using a different physical system based on molecules, and we want to build it in a scalable way by making these molecules in optical tweezer arrays. The reason we're interested, we think that molecules are a great candidate for qubits because the large variety of internal states exist for the molecules. These different internal states are coherent in nature and they are isolated. They can be isolated easily. And these different internal degrees of freedom allow separating the different required tasks to different parts of a single quantum system. For example, we want to have stable qubits for storage. For example, we could utilizing the nuclear spin degrees of freedoms as my qubit 0 and 1. But we also want to entangle qubits. That means we would need them to interact. And for us to interact two qubits, two molecules, we will utilizing different degrees of freedom, for example, rotation degrees of freedom, such that we can first utilizing internal molecular coupling to bring this nuclear spin degrees of freedom, map it onto a rotation excited state, and through dipole-dipole interaction to allow entanglement and coupling of the two molecules that are in, say, opposite parity states. Okay, so in molecule, we can find these three levels to fulfill the task. In a realistic molecule, especially let's say we make the choice for calculation for sodium and cesium, there's not just three states, but actually a lot more, as I shown here. So we can pick out two states out of, say, 32 from this ground rotational states and pick out one from out of this 100 states in the rotation excited state as our three levels for the this dipolar exchange gate that I have briefly mentioned. Now, with a relatively closely spaced two molecule that we can make with optical tweezer, this will allow an interaction exchange time of sort of on the order of 50 microseconds. The fidelity will be quite good, but limited by the fact that these nearby levels are quite closely spaced. In order for us to go beyond these off-resonant excitation, we can simply wait longer for the gate. And as I shown in this calculation, if we go to a time scale of milliseconds, then we can go with the fidelity or the infidelity to be below 10 to the minus 4. We have also considered a number of different sort of physical parameter, experimental parameter to see that we believe to quantify them and see how well we had to control them. And we believe that we, with this distance, we can ultimately achieve a very, very high fidelity to infidelity of 10 to the minus 4. Experimentally, we have been pursuing approaches to gain individual particle control of molecules. And we want these molecules to be in the vibrational ground state for the reason that these molecules in this state will possess a very large dipole moment. We also want to work with molecules in the motional ground state, motional of the confining potential, because the dipole-dipole interaction depends sensitively on their distance of the molecules. And therefore, any jittering, any jittering due to motion, due to the uncertainty of which motional state that the molecule is in, would ultimately cause an error, an infidelity, a source of infidelity. Okay, so there are a number of different approaches that several groups are pursuing. For example, one approach that we have been working on for a number of years is to assemble molecules from atoms, starting with single atoms, assemble them into molecules. We can also gain individual particle control of molecule by directly using optical tweezer to grab single molecule out of an ensemble of laser-cooled molecules. Here I show you pictures of individual molecules. This is work done in a collaborative work in the Center for Ultracold Atoms in John Doyle's lab. Of course, naturally, one could also gain single particle control using molecular ions, and a lot of advances had already been made in this system. Now today I want to focus on the techniques of assembling molecule for atoms. When we think about making molecules from atoms, we think about usually start with an ensemble of atoms, species of A and B, and through collision, molecules could form. But in order to get the single particle control right away, we start with not an ensemble of atoms, but an individual atom to make a molecule. The specific physical system that we work with is sodium cesium atoms making sodium cesium molecules. And this picture in the middle serves as a bit of an outline for what I will be telling you about, where we can now trap the single atoms, using optical tweezers. Here are the images of the two atoms side by side. We can merge them and associate them into a weakly bound molecules, symbolized by their kind of a long distance bond between the two atoms. And most recently, still unpublished work, we're now able to transfer these molecules all the way to the vibrational ground state where the two atoms are stuck together very closely. Okay, so let me tell you a little bit more detail about each of these steps. In order to make a molecule that has a dipole moment, we have to have two different species of atom. So we can, we need to trap and manipulate two different species, and we're utilizing a pioneering work, well-defined, pioneering work in atomic physics, where we can trap single atoms by tightly focused laser beams into a vacuum chamber and overlap it with a laser-cooled ensemble of atoms. We use two different colors in order to individually control two different species, and this is the result as we can image these single atoms. we can repeat these experiment many times and plot out a histogram to cleanly define a threshold to distinguish loading a single atom versus loading 0 atoms. And we see that about 30% of the time we're able to load a single sodium and a single cesium atoms in the in a single shot. Now, to make molecules from these atoms, we face the challenge of two folds. And the challenge are, the first one is, if we want to make a molecule, which ultimately the two atoms will have an average spacing of on the order of 4 Bohr, we start with atoms that to sort of the best of our ability, when we confine them in optical tweezer, the best of ability to pinpoint the position of one atom will be the 0-point motion, which for sort of micron size confinement, that will be about 1,000 Bohr. Now, if we have two atoms in here, put two atoms in the same trap, both cool down to the motional ground state, the probability of finding that two atoms at a small distance of 4 Bohr is very poor. Secondly, for converting atom into a molecule all the way down to the vibrational ground state, we will need a molecule, we will need to remove a large amount of energy. That's equivalent of, say, 6,000 Kelvin worth of energy. So the challenge is, simply put, to be efficient molecule creation while staying cold. Luckily, there had already been a solution that was put forth more than 10 years ago. And these solutions involve two steps. One is to bind the atoms into a weakly bound molecule. So these weakly bound molecules still look kind of like atoms through a scattering resonance called Fano-Feshbach resonance. And these Feshbach molecules allow preparation of this, prepare these atom pair into a single quantum state. Subsequently, the second step is to use a 2-photon coherent transfer process to bring the population from one molecular state, the Feshbach molecule state, to the rovibrational ground state. And in this process, the stimulated photon takes away the excess binding energy. Okay, so when we think about making molecule, that may just be even a little bit more specific about the quantum control. When we think about making molecules from atoms, we don't think about the atom. We most conveniently think about the atoms as pair. So we look at these atoms in terms of its center of mass motion and its relative motions. And each one of this is a ladder of harmonic oscillator levels. When we think about molecules, we again think about its motion, its external degrees of freedom, and its internal degrees of freedom are rotations and vibrations. So in a molecule association process, for example, the magneto-association process, we can then map one quantum state, atom preparing a single quantum state, single external state, single relative state, onto a molecule in a single quantum state. Specifically, we prepare molecules, or actually atoms first, in the absolute ground state, so ground motional state and ground relative motional states. We then, through the magneto-association process, map that to convert that into a molecule where its external state and rotational states are both in the ground state. Vibration states are not in the ground state, but in a single vibrational level that is defined by the Feshbach resonance. Now, if we have one relative motion excitation, one quantum of excitation, we can also map that onto the molecule, and that would, for example, create one quantum of rotation. So after we preload the single atoms, as shown in this picture, we now need to prepare the atoms in their motional ground state. And we can do this by Raman sideband cooling, as shown with our data shown in the picture here, where we can do a pretty good job to bring cesium and sodium to their respective three-dimensional motional ground state. We then merge the two atoms into a single well, very carefully, and not causing much heating, and bring the two atoms at a single location in a single optical tweezer. At this point, we can convert the absolute ground state atom pair into the external and rotational ground state of a feldspar molecule. And this is done shown in this picture by ramping a magnetic field to allow atom to pair up into a molecule. This is the picture of our experimental setup, and you can see our glass cell here are a large pair of magnetic field coils and our microscope objective that allow us to focus an optical tweezer to a tight spot for trapping single atoms. Okay, so we can scan these magnetic field, ramp it through a certain range, and at some point we can see we can cross the resonance, which we identify to be here, and the atoms disappear. The reason the atom disappear is because we actually form the molecule, and our detection is only sensitive to the atoms. In order to make sure the process is adiabatic, we can vary the REM speed REM speed, and we can see at a reasonably slow speed, we're able to have a larger depletion of the two atoms. But to make sure that these are not actual loss, just in a molecular state where imaging light is not sensitive to, we can then do a reverse process to a two-way ramp to bring the molecule back to atoms for image. And you can see that we recover, in certain parameter, we cover most of the population. These molecules live for a few milliseconds. Now, a few words about the external state control. The molecule that we made has a conversion efficiency of roughly 50%, 40 to 50%. And this efficiency is determined by the relative motional ground state population of the atom pair. Basically, only the atoms that are first prepared in the relative motional ground state can be made into molecule, and that limitation depends on how well we can cool the atoms into the motional ground state and bring them together while keeping them in the ground state. Now, because only those molecules can be made into, only those atoms can be made into molecule, the molecular state purity for the internal state is pure by design. And the external state is determined by the center of mass motion state population of the atom pair, and we have characterized the atom motion and deduct the motional population of 77% for the molecule. Okay. So now with these molecules in a single quantum state, in this potential energy surface, they're still way up high here in energy landscape. So our next step is to bring these molecules all the way down through a two-photon process to the rovibrational ground state. This requires us to find a magic bridge that not only have a large Frank content factor to allow this process to be efficient, but also to allow us to convert a predominantly triplet in character feldspar molecule to a singlet rovibrational ground state molecule. So we look for these transitions. We can identify transitions in this potential shown up here and its structure for that particular vibrational level. We pick a particular line that allow us to have the right selection rules to go down to the rotation ground state. And to go down to the rotational ground state, we use a particular pulse sequence of the following. Basically, we treat the problem as a 3-level system and coupled by the 2 laser, omega 1 and omega 2, for a very special condition where these 2 laser frequency is different by exactly the energy difference of 1 and 2, so delta equal to 0. We have one special eigenstate that is only composed of the bare state of 1 and 3. With their coefficient depends on the intensity of these depends on these coupling. So the process that we use to transfer population from 1 to 3 is the following, where we start with very high intensity to collapse the wave function to the bare state of 1, and ramp down the intensity while ramping up the intensity of omega 1 to transfer population to 3. Now, in order to, we can do the reverse process then to transfer population back to 1. Okay, so here I want to show the data. As we scan this relative frequency of the lasers, we saw that we're able to make the signal disappear, doing a one-way STIRAP center around this frequency. And that is because we are now able to transfer these molecules all the way down to the rovibrational ground state. But in order to make sure that these are not lost, but just dark to our imaging sequence, we do a 2-way STIRAP pulse to be able to show that we are able to bring also these populations back for imaging. So now we have completed this step where we can do the internal state transfer to create single molecules in the rovibrational ground state and predominantly in the motional ground state. Okay, to summarize, we've demonstrated control of neutral molecule at the individual particle and single internal and motional quantum state level. Next, we will begin to scale up the number of molecules with the number of optical tweezers to begin with and parallelize these assembly process. And that will allow us to have at least 2 molecules or more, 10 or 100, that we can show that we can actually begin to entangle them. In the future, we want to harness these molecular intrinsic interaction and reach internal degrees of freedom for quantum simulation and computing applications. Last, I wanted to give thanks and acknowledge the team members who have contributed to this work. Here's a picture of my current group, and the people who have contributed to the work are the people at the bottom row here, and also the top 4 the top 4 names of this past member list. I would also like to thank my collaborators and funding agencies. And finally, I would like to also thank for your attention, and I'd be happy to take any questions. Thank you.
Great. Thank you very much, Kuen. That was a fantastic talk. Now we get some time for questions. So the audience, please just type in your questions, ask them. Maybe I can start with a question actually very much from the beginning. I was wondering, these molecules, they have these very nice dipolar interactions in between, and you can use them for gates. But I was always wondering a bit, these interactions are probably always on, or can you switch them off and control the interaction?
So that's a very good question. So there are different ways to switch them on and off, and the way that we're envisioned are actually not require an electric field, so not polarizing them in the laboratory frame, rather to use that the molecule in opposite parity states, and they have a transition dipole moment that allow, as long as we prepare them in the right state, the interaction turns on, but we can bring them out of those interacting states just by, I mentioned a little bit about this internal molecular coupling to go from a rotation excited state to a rotation ground state, but a different spin state, a different nuclear spin state, to allow basically no interaction for the information storage and only allow interaction to happen by driving them into the right rotational state.
Okay, great. And these gates that you described, over what distance is that? So how close?
Yeah, so for sort of the fastest time scale, we were envisioning sort of on the order of micron, and we found that it's really good, but it's too fast in terms of that it will have off-resonant excitation just for the fact that these nuclear spin states are very close by. But there are certainly other molecules where it also contains the electron spin, not just nuclear spins in the ultimate molecule, and in those cases, the spacing of nearby levels are farther away, and that the speed limit would not be it will have a different speed limit.
Okay.
Yeah.
Great. Yeah, I just take an opportunity to ask another question here. So this is really fantastic, these latest results on the motional ground state and the rovibrational ground state. I think this is wonderful that you shared that here. How do you know that it is really the rovibrational ground state, that there is nothing lower? How do you identify that? Is it like a forest of resonances that just stops and that is the ground state?
Yeah, so this usually we follow spectroscopy that had been done before us, and especially in our case, Tiemann and Hanover have characterized the electronic ground state potential really, really well. So the uncertainty to those levels are only, in our case, actually only a few gigahertz. Wow. So we know it to that well, and then we search in that range.
How close?
The spacing of vibrational level would be on the order of terahertz. So so their spacings are really far, and then the uncertainty of the final one is on the order of a few gigahertz. So so by all these spectroscopy before us, we know that this is the rovibrational ground state, and that has been the case since the KRB work in Gila. That's how we found it, and then subsequently many other groups also had made different bi-alkali combination, and that's usually the procedure. So we're confident.
Okay, wonderful. So here's a question from Marian Kupczynski. How are you making these images, photos of closely approached atoms?
Photos of closely approached atoms. You mean that? I assume that probably means the merging sequence. Yeah. So basically, we can calculate, given our trap parameters, the intensity and the pointing, to calculate the potential for each atom, and then we can find a sequence where we can basically just sums of these potential as we move them, and how, as we steer basically the position of this potential, the atoms will follow the bottom of the well. So this is just a calculation of what the potential is doing, and we expect the atoms to follow the bottom of the potential in that case.
And then the imaging is just fluorescence imaging, where you can actually image them separately, right?
Right. So when we image them, we're usually stationary at one point. So sodium and cesiums are side by side at a certain distance, and we usually bring them back out to a certain distance to look at their survival.
Yeah. Okay, great. I think we have to wrap up. There's another panel starting after this. Thank you very much, Kuen. A great talk, and thank you so much for showing these very recent results. I'm really excited seeing those published very soon, I would imagine.
Thank you, Hannes.
Yeah, thank you, Kuen.